Wow, thank you. It's nice to be here again. Last time I was here was February 2020, and then, I don't know, something happened, and that's why I wasn't here last year. So yeah, we're going to talk about Java next, from Ember to Loom, from Panama to Valhalla. And as Brian Getz, who's working on project Valhalla, once heard, it's like there's 6 PhD theses in there. So that means we have roughly 24 PhD theses to go through in about 50 minutes. So this is going to be a little bit of a tour de force, right? I'm not going to give you a tutorial. You're not going to leave this talk and be like, OK, I know exactly how to use these features. Well, first of all, you can't unless you download certain early access builds. But also, I want to give you an impression of what these things can do and where they evolve, because they might change a lot between now and whenever they're finalized. If I'm too fast, or too slow even, you can go to slides.nipafx.dev, and then you will see the slides right there. And you can, you have to click on Java next, but you'll figure that out. And then you can follow along if you want to. It's not the best mobile experience, I gotta say. It works better on laptop. OK, so let's start with Project Ember. We're just going to dive right in. So Project Ember is focused on smaller, productivity-oriented language features. And if you have the slides open, I always leave all the links to the project, the wiki, the mailing list. So if you're interested in one of these projects, it makes it easier for you to get in touch and stay a little bit closer to what's going on. This launched in March 2017, and it's led by Brian Getz. And the motivation is to tackle some of the downsides that Java comes with, right? So Java can be cumbersome. And it tends to require boilerplate, not everywhere and always, but like in specific situations, it feels like, well, I want to express this one thing, but I can't, so I have to write a lot of code. And Ember is not so much a solution as it is, in good Java parlance, a solution factory, right? So the goal of Ember is not to start and deliver a bunch of features and be done, and the project is over, like Project Lambdas and Jigsaw were. No, the goal here is to continuously assess where Java's language could be more expressive, and then deliver something on that. And they've done that already. So this is inverse chronologically ordered. The circled numbers, you might see them on a bunch of my slides, are the Java version in which each feature got finalized. So you can see local variable type inference in Java 10 at the bottom, and then you get a bunch of stuff that's connected: switch expressions, type patterns, records, seal types. You can use each of them on their own, but together they form the larger pattern matching story. And then this would be the place that would lead you into a little bit of pattern matching, and we talk about that. But that has been done a whole lot of times already, and so I brought something new. So if you're interested in pattern matching, you can always come up later and ask. I'm at the conference for the rest of the day too, so you can always track me down and we can talk about whatever you want. But what I'll talk about now is not pattern matching actually, but string composition. Something where something's in the work. So what I'm doing here is I'm trying to compose strings. I have this property and this name variable, and I'll try to put them together into this very, very simple exemplary select statement. So there's 2 ways to do that. One of them is to just use plus, and the other one would be to use a format string. There are a couple more, but they all experience the same downsides, that they're somewhat cumbersome, and they come with 3 injections to boot. That's not great. It would be pretty cool if Java could do something like this, which many other languages can. You just go select star from person P, and then you put in the property and the value variables somehow. You have some syntax way to tell the language, nope, this is not a string, this is an expression. Take the variable value or call a method or whatever and put that here. That would be nice. Still comes with free SQL injection though. So it's really easy now to do the wrong thing. And SQL injections are like a poster child for this, but they're not the only concern, right? There are many other things. Whenever you want to have strings that you want to put something in, mostly these are some kind of structured string. I think there's a talk going on right now that's called There Is No Plain Text, and I have the impression that maybe goes in the same direction. So usually you want to do something like HTML, JSON, YAML, SQL, whatever, and all of those formats have in common that they have to be validated for you to be sure that they work the way you intended to, and they all follow format-specific rules. So it would be kind of nice to somehow have that in this putting strings together while we're at it and inventing something new. And this is where string templates come in. So the idea here is, and now I'm using a text block, but they would work if they turn out the way that they're proposed now. They would also work with regular strings, doesn't have to be multi-line text block. And what we see here is, so a query is defined, and then we have like this text blocks, 3 quotation marks, but there's an str dot before that. And so the thing in the 3 quotation marks with the / curly braces syntax, that is the one that's currently being talked about, doesn't necessarily have to be this, but the advantage is that that's at the moment an illegal character sequence in a Java string, so that's helpful. to use one of the sequences that nobody could have used in the past. So the idea here is that I'm putting the property and the value in there, and that would be the templated string. That's the actual string at the end between the text block. But then I have something else. You know, it's Java. We're going to have like a little indirection there just to make it more fun. And that's going to be the template policy. And the template policy can do interesting things. So for example, STR can just put stuff together. It's just like string concatenate, basically. So here I have another example from the JEP draft, which has a description, and it's basically like a little payment bill, right? So I have a description and a unit and a quantity, and there's even some math going on, a subtotal and tax. And so this would just be like plainly concatenated, put together, and you get this thing at the bottom, which, okay, looks like we got to put the string together in a manner that's less painful with all the plus signs. Now, usually we don't give monetary amounts with like 3 digits, so that's not ideal. So another template policy could potentially be the formatter. And in the formatter, and you can see this is already too long for my slides, I'm sorry about that, you can put in additional information, the one that you use from format strings, like how many places do you want to have before and after the decimal point, and all of that, and now you get a nicer result. And that's a different templating policy. So it's the same thing on the right-hand side, mostly. It's a text block with this embedded variables in there, which is price and quantity and all of those. But then we have a policy that does different things. The string policy just concatenates. The formatter policy applies formatting. But so far, we've just been focused on strings. We always started with a string and ended with a string. But why, though? It's like what we often want to do is create an SQL statement. Maybe we want to have some JSON that we want to have parsed. So what we usually do is we start with a string, put in values, get a string, and then hand that thing off somewhere else, where it then gets validated and parsed into another object that I, as a Java developer, prefer to interact with, as opposed to just blank strings. And why would we go the detour? Like, we have the string and the values. Why do we first dumb it down into a string format or in a text format and then try to, make it a statement again? And this is where custom templating policies can come in. So the idea is that we would be able to create our own templating policies. So that's just a very simple interface, takes as input a templated string, and returns as output a result. A result of any type. Doesn't even have to be a string. And we could all come up with that stuff, and then put that in front of the period before the text block. So for example, we could do something like this. Maybe this will be on board. This could be something that libraries provide. But this would be, by the current proposal, totally doable, right? So we have this SQL templating policy that takes the select statement or the partial select statement string and the values that are embedded in there, and then it does all the things. It validates, it escapes, it makes sure that this is a proper selection, and it returns you a statement, like the Java SQL statement in this case. But like in general, it just would return you a non-string class. That's the interesting bit here. And you could think about doing the same thing with JSON, right? So you have a text block again, and you have a name and a phone and an address. You put that into the JSON document, and what you get back, or rather into the JSON string, and what you get back is not a string. No, it's already parsed to a JSON object. It's already verified and validated that it's OK. And I think that's really cool, because that avoids the SQL injection. That makes it very simple to concatenate strings, while still giving you the ability to not do the wrong thing faster, but do a better thing and faster, which is really ideally the outcome of all of these improvements. That, as I mentioned a couple times, is a JEP draft. So a JEP is the JDK enhancement proposal. That's the process through which Java evolves and gets new features. They're first like drafted, and then a lot of things can change. Then the JEP itself is finalized. Still, things can still change. At some point, it's a preview feature. Things can still change, but the amount of change hopefully drops down a lot, and eventually the feature is finalized. And that's one of the things. So this is very, very early. Like, there is a non-zero chance that none of this will make it, but I doubt it. I'm hoping that this will be seen in maybe 19 or 20. And also, Amber is working on other stuff, right? It's working on finishing pattern matching. That's the third preview in JDK 19. There's the idea to have more patterns. For example, JEP 405 goes into that. There are some ideas about concise method bodies, and even like redoing serialization, for which there's only a white paper, which is probably even, I think, the step before the JEP draft. And all of that's something that Project Amber has been working on to overall make Java more expressive, reduce the amount of code we have to write, and hopefully make us more productive as developers. And now, if you're like me, you're wondering, that's all very nice, but so when do we get to play with that? And so if I ask my colleagues, the answer that I get is, when it's done, hopefully soon, which is, to be honest, the only the only valid answer that they can give, so I don't dig deeper. Instead, I make up my own guesses. And I'm going to share them with you because all of my colleagues are currently in a meeting, so they're not here to yell at me. So these are my personal guesses. Imagine there was like a huge safe harbor slide. If you bet money on this, it's not my fault. You cannot sue me, I'm poor. Well, not by Oracle standards. So these are my personal guesses, right? Just to give you an idea what I think is when this is going to happen. And this is based on public information, right? So if you look at the mailing list, if you look at the JEP drafts, you kind of get a feeling of how far they're progressed. So this could be all totally wrong, but I'm somewhat confident in that. So I think next year we're going to see patterns finalized. We're hopefully going to see the first preview for deconstruction patterns, if you know what those are. Template strings, as I just showed you. Hopefully the first preview next year sometime. And I'm pretty sure that we're going to see more patterns under this whole pattern matching umbrella in 2024. And then Amber is kind of like a magic black box where sometimes something comes out, you're like, oh, I didn't know they were working on that. That's pretty cool. Like the template strings. I didn't know that was in the drafts or even being considered until I saw the JEP draft. So I'm pretty sure there will be more stuff probably like in 2 years' time that I don't know about now. So I'm looking forward to that. Once again, if you have the slides in front of you and if you're interested in these topics, I give you, usually at the end of each chapter, I give you, or section, I give you a selection of the best places to start getting to this, besides all the JEPs that are linked. These JEPs, the JDK enhancement proposals, they are great. They're written as a technical document, and they're not exactly addressed as regular developers like us. They're mostly like to the OpenJDK community to understand that feature, but it works well. Like it's really, they're usually written very well and very easy to understand. Well, not very easy, but easy to understand. So I can only recommend reading the JEPs directly. Although if all of you do that, I'm out of a job, because that's mainly what I do. I read the JEPs and tell you about them. So I'm just going to bank on the fact that not everybody's going to be doing that. OK, so let's talk about Project Panama. Totally different project. I'm going to abandon whatever we just talked about. Project Panama is about interconnecting JVM in native code to make it easier to do things that are closer to the metal, so to speak. Once again, all the links launched in July 2014, led by Mauricio Shimamura at the moment. There are different sub-projects. There's the vector API, which is like totally its own thing. And then there's the foreign memory and foreign function APIs, which are connected, but you can view them separately. I want to talk a little bit about vectorization. I even brought a code snippet. So let's consider you have this computation to make, right? So you have, you want to compute the number C by squaring A and squaring B, adding the things up, and then get the negative of that, right? So that's some very basic numerical operations. But you don't just do that for one number or for one pair of numbers. You do this for a pair of input arrays, and you want to have an output array, right? So you want to have A and B as arrays and C as output. So the simple way to do this is to write a loop. You just go from the beginning to the end of the array. Now, they must all have the same length, of course, for this to work. And you just type out your operation. And that works pretty well. Obviously, delivers the correct result. And then the just-in-time compiler tries to be smart about this. And it's like, you know what? Like, we don't have to do this one step at a time. Because modern CPUs have so-called multi-word registers. They can be as big as, I think the laptop has 512 bits. My Ryzen at home has 256. And that means you have one register where 512 bits could be in there. So that could be up to 16 floats. And then you can store 16 floats in that register and 16 floats in that register, and then say, do an addition, and you get 16 results, and it takes about as much time as a single addition would. This is not parallelization across different CPU cores. This is the same CPU core doing just like one gigantic operation, but instead of a bunch of small ones. And this is amazing, right? So this is, if I understand things correctly, this is something like the MMX extension back in the days on Pentium. I don't know when it was, 90s or something, was introducing. And the idea behind this is single instruction, multiple data. SIMD, that's the key word here. And just-in-time compiler tries to find these loops and tries to figure out, oh, that loops, it looks like I can do that with it. So it like unrolls it and tries to auto-vectorize it. And that works, but isn't perfect. It's not 100% reliable. And the vector API succeed at making that reliable. Now this looks very different from what I just showed you, and we're not going to go through all of that code. The interesting bit is here that at the beginning, I'm trying to figure out, like, I want to have a vector of float. So that's like how many bits do you have, how many floats fit into one register, that's that part. And then you pull the stuff out of the arrays into this vector here, and then you go A times A, add B times B, and then the negative. Right? So you can see the arithmetic computation there, you store it back into the array. That's what this code does. Again, you don't have to look at this and be like, I'm done, I'm going to do that at home, just to get an impression of what this looks like. And if you just looked at it for like 30 seconds, you might think that was not very clear and concise. But given the requirements, I actually think it is pretty much that. And it's platform agnostic. It works across all kinds of CPUs. And the just-in-time compiler will reliably turn that into the optimal machine code for your CPU that this is running on, not that you're building for, but where this is running on. And if the CPU doesn't have these kinds of features, it says graceful degradation, meaning you're not going to get performance that is worse than the loop, or at least not much worse than the loop. So you will always have, like, as a minimum bar, basically the loop performance, but it can be much better. So if you're doing kind of image manipulation, or if you're doing image manipulation but you don't do the code, write your code yourself, the library that you're using might jump on this as soon as it's possible. Okay, now we're going to leave the vector API behind. We're going to talk about the foreign APIs. And I'm just going to go over this very quickly, mostly because I'm not a C or C++ programmer, so I'm already out of my depth just mentioning this. So if you find any mistakes on the slides, do tell me afterwards. The idea behind the foreign APIs is that some things that you want to do with Java at the moment that are a little bit outside of the JVM's immediate influence are tough. For example, you want to store stuff off heap. You just think, like, I can do garbage collection better than the garbage collector, or I want to interact with native code, so I want to put stuff off heap. At the moment, you would use byte buffer. That's limited and not very efficient. Or you can use unsafe, which, as the name suggests, is unsafe. And it's not supported either, so that's not great. But you have this like decision to make. Do I do it the right way, or do I do it the fast way? And then you have Java native interface to call into native code. That involves a lot of different artifacts and tools that's not exactly reliable and easy to get right. And also, it doesn't reconcile the different type systems between Java and C. And this is where these two new APIs come in. The foreign memory API addresses the first point. It makes it easy and performant to put stuff off heap and get it back. And instead of just having one class, the byte buffer, and do everything with that, it has a more involved API that gives you much more influence over what you want to build and makes it smarter for you to say, like, I have a point array here, I want to get a point out, even though in reality it's just like ints, pairs of ints back to back, stuff like that. So you have classes to allocate, you have classes to access and manipulate, and very interesting, you also have classes to deallocate. There was a problem with JNI, and with byte buffer, where you have 2 gigabytes of something off heap, and you lose the reference to the byte buffer on purpose, so you're expecting the garbage collector to collect the byte buffer and free up those 2 gigabytes. The garbage collector is like, well, that's just a single reference. Like, the byte buffer is super small, so it doesn't have like a high urgency to clean that up. And so you cannot actually easily deallocate. You will just have these 2 gigabytes blocked somewhere until an unknown point in the future. And the foreign memory API attacks that head-on, giving memory sessions that you might just have in a certain scope. You might only scope them in a certain thread, which makes access more safe and performant. So all kinds of stuff that's in there. And the foreign function API wants to make it much easier for you to call into native code. So the basic idea is to use method handles for that, which is what these classes CLinker and function descriptor, what they try to do. So they give you a very low-level API, and you can create that with a tool. So the idea is use a tool to create out of a C header file a very like a very low-levelly, but in Java created API, a Java API, and then you write your API as a layer on top. And every time the library changes, you regenerate this low-level Java API, and then you get all the compiler errors where types don't align, whatever that you would ideally want. From a type-safe language, and then you keep coding from there. This timeline is not my guess. This is the official plans are for the foreign function memory API to start previewing in 19. I'm pretty sure that's going to happen. And the vector API is basically done, but it needs to wait for Valhalla. It needs primitive types and universal generics to really shine, and so it's basically blocked at this point, which is a bit unfortunate. But I think it's for the best for the API to not come in, and then a year later with Valhalla, we'd be like, oh, we would do this completely different now. Once again, more links for vector API and for the foreign APIs. The design documents here, by the way, they're really great. So these are not the JDK enhancement proposals. These are like dedicated documents to explain a little bit better of the motivation and the background. And so these design documents, when they exist, are usually really cool too. Okay, let's go to Valhalla. Valhalla is about advanced Java VM and language feature candidates, which tells you nothing, really. I think the better description is that it wants to overcome the split in Java's type system. So Java's type system is split between primitives and classes. Primitives are like the 8 types that are there, and we can't do anything about them. And then we have classes which we can create our own instances of. But all the classes that we create have 2 things. They have identity, and there are references. And that gives us a couple of properties. So for example, everything that has an identity, so what do you mean to have an identity? If you write int 5 and then another int 5, it doesn't make sense to ask how are these 5s different. Oh, they're ints, they're the same 5. Like, even the question doesn't make sense. But if you write new integer 5 and new integer 5, then these are equal. I mean, they're both 5, but they're not identical, because if you write new integer 5 equals new integer 5, the result is actually false. So this is what's called identity, right? This concept, and that comes with extra memory for the header, because you need that to manage the identity. It gives you mutability. You can only change stuff that has an identity, because otherwise you would change the entire thing. It allows locking, it allows synchronization, gives you all of the big hammers that Java has in its toolset, but not all custom types need that, right? Some of them are totally fine not having identity. And then they also all have references. References mean that you have a memory access indirection. You don't store, if you have an array list and there's a backing array of integers, you don't store the int values, the actual numbers, in the array. If it's an integer array, what you store are pointers that go, if you're in bad luck, all over memory pointing at your actual numbers, which is not great. That also means that they're nullable. Like if something wants to be nullable, it needs to be a pointer. So the pointer can express, I am no pointer, I'm the null pointer. It also protects you from tearing, which is not something we want to talk a lot about today, but if you know what that means, it's like it's important to get to cover that as well. Okay, so also not all custom types need that. Actually, Valhalla had for the longest time, the question is, how do we reconcile that? Okay, we agree that we don't always need identity. But what about reference style? Like, do we need things to be nullable? I mean, sometimes, even though it hurts me to say it, people do, me included. So the current proposal for Valhalla is actually more complicated than the previous proposals in the sense that it tries to reflect that. It tries to reflect that, yes, there are types like that we will call value types if this proposal goes through, that say, I don't need identity. But maybe you want to go further and also give up references. That's all primitive types. And then universal generics will allow you to use our custom value types, our custom primitive types, and all the primitives that the JVM has as a generic type argument. So you can write something like array list of int. Now that only allows you to do that. There might still be boxing involved. You do want to avoid boxing to get all the performance, and that would be specialized generics. So specialized generics see the array list of int and turn that into a backing int array. That's the interesting bit here, and that's the biggest ticket item. I want to guess that at least 4 of the 6 PhD theses are probably in specialized generics. At least that's my understanding. Okay, let's have a look at each of these very quickly. So let's start with value types. Value types, I made a rational number up here, which is a nominator and denominator. And you probably have to create the fields yourself, but they will be implicitly final. You have to create a constructor, you can have accessors, all that kind of stuff. And you can basically use all the class building mechanics like implementing interfaces, adding methods, all of that. But you will not have the ability to have all kinds of superclasses. So the kind of superclass that you can have are somewhat limited. There's a long list of limitations. But other than that, you can do whatever you want, like with records, for example, right? They can be very simple, but you can add a lot of stuff if you want to. The behavior, as I mentioned before, is they don't have identity. And that means that some of the things that you can do based on identity, like synchronization or locking, for example, that's something that you cannot do anymore. So you would get runtime exceptions for that. And the identity check doesn't make sense anymore, like the 2 equal signs check for identity, but we don't have identity anymore. So instead, it compares by state. The benefit of that is that, first of all, if you like a more functional style of programming, you get guaranteed immutability. Also, the JVM knows that these are guaranteed immutable, which normal final fields, it cannot actually make that assumption because they can be changed with reflection. This will not be possible here. It also makes Java more expressive. If you do something like domain-driven design, you will now be able to say this is a value type. This is a value that I want to express here. It's not like a class that looks like a value that or use an annotation that says as much. No, it's a value. But the probably most interesting part about that is that it allows the JVM to apply a bunch of optimizations. It doesn't have to track identity. It doesn't have to be sure that, oh, that string, well, string is not going to be a value type. But that instance is actually the same as the instance that like half an hour ago you created a lock on and have to track all of that. It doesn't have to. So it can destroy and recreate instances as long as the values are the same, and that's fine. But there are still references. That means you get null as a default value, and also you get protection from tearing. And the idea is that the JDK classes that are currently marked as value-based classes, that concept was introduced in JDK 8, optional is value-based, the local datetime, the new datetime API that was added in Java 8, all of that is value-based, and all of those will hopefully be able to migrate to these value-based classes in JDK, in the future JDK version. That also means that if you're locking on an optional at the moment, this might throw a runtime exception in the future. Isn't that backwards incompatible? No, because optional said I'm a value-based class, and that's a link, and if you like the Java doc, and if you click that, it tells you value-based classes, you're a bunch of operations that you're not allowed to do on them. I wrote a blog post about that back in the days. If you never heard the concept of value-based class, I recommend to Google that, and then you land on my blog post or somebody else's. They're probably all doing a good job explaining what you're supposed and not supposed to be doing with them. Or you just read the Java doc. Next step, primitive types. Look a lot the same thing, right? You just write primitive instead of value there. It's almost the same thing like a value class, all the same limitations. In addition, you cannot have a field of your own type. You cannot create a circular reference there. Once again, that's like a low-level detail. I want these slides to be complete and not give you like the wrong impression, like with tearing, but also I don't want to go overboard and explain all the details. It's just something that if you're interested in, we can talk about later if you want to. Like value types, primitive types have no identity. So all of that we just said applies. Also, there are no references. That means we can have a null. Instead, the default value is all fields set to their default value. And then the question is, when is that okay? So I just showed you the example of a complex number. A complex number has, in one of the presentations, a rational and an irrational part. And if both of them are 0, you just land in the 0, and that's fine. That's a great default value. If you have a rational number that has a nominator and a denominator, you don't want the denominator, that's the thing at the bottom, right? Well, the thing at the bottom, you don't want that to be 0, because that's an illegal number. So it would be weird to have as a default value an illegal number. So that's why maybe the rational number could not be a primitive type. That would be one reason. And also, primitive types can tear into concurrent assignment. But the JVM can go much further with performance, not sure about much, can go further with performance optimizations to the point where primitive types that we declare will perform in the same ballpark as today's primitives. So you create a point that has like 2 integer fields that are the x and y coordinate. When you start writing methods on that add 2 points or subtract 2 points or whatever, and that will be the same as if you optimize and put like these 2 ints into their own like arrays. So instead of an array of points, you would have an array of like x coordinates, an array of y coordinates, so they can then do the math there. You would get the chance to write the code that you want to write and be as fast as the optimized code otherwise. Now let's have a look at the clock. Yeah, I'm going to skip a little bit on the primitive boxes. Basically, the idea is that just like there's int and integer, for primitive classes, you will be able to also have kind of a box for these primitive types. And the idea is then that this concept of we have primitive types, and there can be a box, or there will be a box for each of those, to apply this to the primitives as they are today. So primitives will migrate to this new concept as well. Of course, there gets a couple, a number of special treatments to make all of that work perfectly because, well, it's called lowercase int, and that's a keyword. So it's not 100% identical. But the idea is basically dog-fooding this idea and or this concept and make sure that it's strong enough that it can even carry the current primitive types as they are in there. And then we would actually, you could still reference to integer, of course, but the code that is in the class integer will then move into what is then effectively the primitive class int, and that means int gets methods. You can call 5.toString, not new integer 5, just 5 to string. That's pretty cool. I mean, it's not terribly important, but I can maybe stop, if I have a number and need a string, I can maybe stop having an empty string plus the number. Because that always makes me feel dirty, but it's the best way to do it, I think. Okay, anyways, I'm not going to go into generics a whole lot because most of that happens inside the JVM, which is way beyond what I'm capable to understand, because that's complicated stuff that goes in there. But the idea is that you will be able to use the primitives, but also your own value types and primitive types in generic type arguments, and that will just work. So you can now generify, not now, we will then be able to generify over all types, and that rift in the type system between primitives and classes is mended. Generics, you can use all of them. You can create methods for all of them. You can have custom primitives, you can have custom classes. So the entire rift is healed. And then specialized generics wants to go in and say, OK, now we're also going to give you the performance as if you hand specialize. So all of this in-stream and long-stream and double-stream and int2 double function or whatever, and then the Eclipse collections that have specialized collections for primitives. All of that, ideally, is unnecessary because the JVM or the just-in-time compiler can do that. It can give you just the regular compiler, I guess, at this point. They can give you that kind of specialized performance out of the box. Eclipse collections do more. They have like their int list has more methods that would not be on the list, so you cannot necessarily replace all such code with that, but a lot of that hand specialized code will go out the window, which is great, right? Less maintenance means a little faster pace. So overall, Project Valhalla introduces value and primitive types, plus universal and specialized generics, to give you overall fewer trade-offs between performance and design. You can write the code that you want to write for readability and still get good performance out of that. You don't need manual specializations. That was my Slack. You get, like, if you don't use any of these things, you will still get better performance, right? Because some things within the JVM can make use of this. You can express a design more clearly. And I think once we get to communicate more between different parts of between different subsystems of a larger system, by pushing value types or primitives back and forth instead of potentially mutable classes, I think this will make stuff more robust. One way how there's unwanted interaction between different subsystems is usually because you pass something mutable around and it got changed into places and you didn't track it properly. And that's something that this can potentially fix if we then use more value types and primitive types in our APIs. That's more like a long shot. I think the first part are more important. Java becomes more expressive and performant. These are like super sketchy, these guesses. So this, I think, Valhalla has like the highest uncertainty in all of this. I hope to see value classes preview in 20. Like, cross fingers. And then shortly after that, probably primitive classes, the primitives as classes, which is like, int becomes that, and then the universal generics. I think, so my basic understanding is that these four really make the most sense when they arrive very close to one another. Specifically, these two, the primitives classes preview and the primitives as classes preview. So JEP4 1 and 4 and 2. And then specialized generics, I don't know, probably down the line. It's just like, so over the next couple years. Once again, lots of links. The State of Valhalla documents are amazing. The Road to Valhalla and the language model, that's straightforward to read and to understand. The most complicated part is one weird diagram that I had to study for like half an hour until I finally got what it was trying to tell me. But that aside, like, they're great documents. I read the JVM model and gave up. But that's also there if you want to dive deeper. OK, time for a little ad break. There's much more going on than just these large projects, right? We had lots of API additions and changes. I'm not going to go over the entire list. Just to pull out one thing that I found very interesting, this Unix domain sockets. So if you're running processes on the same machine, and you want to communicate between those two, you don't have to use a loopback anymore. You can use Unix domain sockets, which are faster and safer in the sense that they don't open a connection that can potentially be reached from the outside world. And Unix domain sockets are also supported in Windows, which is why Java could pick them up. And lots of internal refactorings as well that make the code more maintainable and faster. There's a bunch of usability changes that were made. For example, UTF-8 is now the default. That means if you're on Windows, and you don't pass the encoding on to all the APIs that can accept one, you're probably going to see a change in behavior if your files are then also not in Unicode. There's stuff like the simple web server. You can now write JWeb server since JDK 18 on your command line. We'll start a web server in the current directory, which is, well, a small little tool, not a life changer, but very interesting definitely to have. This is what's running. This presentation runs in the browser. Let me put the focus in the right window. So you see that runs in Chrome, and that's actually JWeb server powering this at the moment. We have performance improvements always. Like there's always like the smallest refactorings, like string formatter, for example, got a lot faster to like continuous improvements on all garbage collectors. The class data sharing archives, you should look into class data sharing if you pass Java 11 and check out what you can do there to improve launch times of your app if you care about those. There's always, of course, security work going on. For example, context-specific deserialization filters. So if you do deserialize content that comes in, or objects that come in, you can use that to prevent deserialization if they don't have the right format that you expect. And then one thing that is a little bit newer over the last couple of years is that we also actually start to see things getting, goes the way of the dodo. Like arm activation and Nashorn and the concurrent mark sweep, these are all already out and gone. So if you're on 11 and looking at 17, then those are things that are already gone. And then there are a couple of stuff that's deprecated. Finalization, security manager, applet API, and bias locking. They still are in there to different degrees. You need to have to activate them if you want to still see them, or you can add a command line flag that deactivates them. So for example, finalization is still on. But if you wonder what would my app work like if I hadn't finalization, you can turn it off with the command line flag, and then you can observe your app with the profiler and see, does it close the file handles? Do things still work as I expect them to? And if not, that means there's a resource leak that gets patched by a finalization. So wherever that resource leak comes from, that should use a different approach. And I link to all the jabs. They're always going to detail on what the background is, what the motivation is, what the fixes are, what the command line flags are. They don't talk about a specific timeline, but my impression is, like, for example, security manager, that will not be gone in 19, right? So that's like the very careful first steps, letting the ecosystem know this is something that's going to go away, and it's probably going to be years before this is going to be actually removed. Generally speaking, to make migrations easier for you, stick to supported APIs, stick to standardized behavior. Don't just try out what the JDK is doing and then rely on that. Read up in the documentation if that's actually what it promises, or if you're accidentally relying on implementation detail. If you can, stick to well-maintained projects. That really makes a difference between a project that is done like I have a small little open source project and I don't have all the time in the world to maintain it. So if something critical happens where it would break on new Java versions, it could take me a while to fix it. If you stay with, let's say, Spring, they're probably faster than I am because they're a larger team. Generally speaking, that's always a good idea, security-wise as well, also performance-wise and feature-wise. I know it's extra work, and I understand the limitations or the downsides of that, but try to keep just like everything up to date. If you want to see what's coming down the line, or rather what's being removed up the line, that would be JDepreScan for you. So that's a command line tool that you can use that analyzes bytecode and tells you, well, this class uses that deprecated class, and that class uses that deprecated class. And the great thing about that is you can run that on your code, but also, of course, on all your dependencies. And then you get like a complete overview of what things need to change, and then you can reach out to those projects and be like, hey, are you aware finalization is going away? You have a finalizer here. Would you consider removing that? That kind of stuff. So I want to have a question about adoption. Oh, I shouldn't show you that before. OK, so I want to ask about which Java version you're on. OK, so the question is basically, what is the newest Java version that you run in production at the moment? So who is on 7 or below? I see literally one person. I'm sorry for you. Maybe there were more, but there were like very few people. That's great. OK, so who's on 8? That's amazing. So 8 is a great release to be on, and I love it. But I like that it's so low. That was like maybe 15%. It's really hard to guess. OK, so who's on 11? That's a lot of people. I say at least twice. So let's go with like 30, 40%. That should add up to 100 eventually, right? Who's on 17? Wow, that's as many as 11. And now, for those of you who want to earn like extra points, who is on 18 or newer? Who goes with the new releases? A couple people, more than on Java 7. That's good. So a special question to those of you who are on Java 11. Let's say in 6 months, of those of you on Java 11, who will still be on 11? Like, who's not planning any upgrades? Who's like, nope, we looked at that, it's not worth it? Nobody. Wow, this is like, you're the best audience. This is like the best outcome I could hope for. So basically, I come back next year, nobody's going to be on 8 and 11, one on 7, and then a couple people on 20. Great, that's cool. So that was basically what I was going for. So Java 11 is slowly but resolutely overtaking 8. I think at least with the conference audience, that process is behind us. Adoption of 11 from 17 looks good. And they're always using the latest. It's uncommon but persistent. So I think we achieved that as well. OK, we got 10 more minutes to talk about Project Loom. So let's see how far we can get with that. So Project Loom discusses JVM features and APIs for supporting easy-to-use, high-throughput, lightweight concurrency. It's a big one. And new programming models. Let's see whether we get to that. Once again, all the links are here. That launched in 2018. And Ron Pressler already got it mostly done and wrote like half the comments on Reddit. I don't know how the man does that. But he's like, that has been so much work, not of course not only by him, but by a larger team working on that. And that's impressive, right? So Valhalla started 4 years before that. This is faster than Lambda, for example, and way faster than Jigsaw. So we see some really impressive results really soon. So to go through the idea of what Loom is about, I want to start with a motivating example. Say you have a request coming in, right? So you're writing a backend, the request comes in, you pull out the JSON apart, put into Java objects, all of that, authentication, whatever. At some point, you want to query the database, and that's a blocking call. And then after that, the data comes back, you pull out some data, put it into response, send it back down the wire. So how's resource utilization overall within the JVM, within the runtime? Well, it's good for 1 and 3, and for 2, it's really bad. You're just sitting there waiting. So how would you implement that request? Like the normal, like the just run-of-the-mill approach to this is, well, so the unit of concurrency, meaning the unit in which like concurrent requests come in, are these requests. That's what happens in my app logic, my domain logic. Within the JVM, that would be, or within runtime, I tend to say JVM too much, within the runtime, that's the thread. That's also a unit of concurrency. And you can just align them and say, look, I'm going to use one thread for each request. Super simple to write, debug, profile. You can step through the entire request from start to end. It blocks the thread on certain calls. That's what you pay for. Or that's what you pay with here. And that means that since the number of platform threads is limited, you get bad resource utilization and low throughput in certain scenarios, right? So if you have high CPU saturation because you're doing a lot and don't do a lot of waiting, then that's great, right? But in many situations, that's not the situation you're in. You're actually doing very little actual computation, a lot of waiting, and then it can be hard to increase the number of threads to an amount where you can actually keep the cores busy and you're not just sitting around waiting. So asynchronous entered the picture quite a while ago at this point and said, okay, you know what, we have a crazy idea. Let's only use expensive threads when we actually need them, and let's not have them just sitting around in the parking lot doing nothing. But that means you have to use non-blocking APIs, futures, reactive streams, all that good stuff. That is harder to write, but particularly it's challenging to debug and profile. You cannot just step through that anymore. Basically, if you go from a for loop to a normal stream, you feel like, oh my god, debugging just got so much harder. That on steroids is what happens when you take like an asynchronous code and turn it into fully asynchronous code. It just makes it tougher overall. And it's incompatible with synchronous code. If you have an API that doesn't know about all your asynchronous shenanigans and just does blocking calls, you very soon end up in a similar situation where you started. But the good thing about this is it shares the platform threads. You get great resource utilization if you can pull it off and a high throughput. So there's a conflict. Simplicity, throughput. What do you want? Do you want your developers to be productive, or do you want your CPU cores to be busy? I mean, that's oversimplification, but roughly like that's the schism we can see here. Virtual threads come in, and I try to fix this. So the idea with a virtual thread is that it's a regular thread, and that's not just like weird font, that's my code font, so that's trying to tell you it's an irregular instance of the class thread. It has a very low memory footprint, has very small switching cost, and the very important part is that the runtime is in charge of scheduling. It's not the operating system. The operating system has to have pretty steep requirements for when and how to switch threads because it has to isolate processes. The JVM doesn't have to do that, right? It's within its own process, that's fine. So it can do, and it knows more about the ongoing processes, so it can generally be smarter about this. And the idea is that a virtual thread requires no operating system thread while it's waiting. That's like the critical part. A virtual thread can wait for free. It doesn't hog an expensive resource. Now, this is basically the above the line thing that you need to know. Now we go below the line and discuss, like, how does that work, though? So give you a better impression, because at first glance, this sounds like how, though? How would you just do that? And so below what we would immediately use, so within the runtime, the management of virtual threads happens in a way that it has a pool of so-called carrier threads. These are actual operating system threads. And these run the virtual threads. So you have a virtual thread, and as soon as that does something that is blocking, the virtual thread thinks, oh, I'm sitting in this blocking call, waiting for the database. But what the runtime does is it takes away the carrier thread, which is then free to do something else, and parks the virtual thread, and then later it can put, when the call returned, put the virtual thread together with it and send it off, do more computation. So this is what that would look like for the initial example. When we have a virtual thread, then the runtime submits the task to the carrier thread pool with the interpreting the request part. It does the interpretation. It runs into the call where it blocks, and then the virtual thread yields the carrier thread the runtime takes the carrier thread and hands it back to the pool, where some other virtual thread can start operating on it. And when step 2 unblocks, the runtime resubmit the task, and we go on from there. And the important part is that inside the virtual thread that is invisible, the virtual thread doesn't know that. It just thinks it steps through all the commands. So what I did here is like it's a very impressive and also very bad example. So we're creating 1 million virtual threads that wait for a second. Like as a Java developer advocate, you don't write a lot of production code, but that even for me, that is unproductive. But it's 1 million threads. And creating 1 million OS threads and have them wait for a second is not going to do the same thing to your machine as this. So basically, the joke is that virtual threads can wait at infinite throughput, right? You can do this on any, like you could probably do this on your phone. Like it doesn't require any resources, basically. It just creates 1 million threads that immediately wait and don't do anything. So that's pretty cool. But you probably want to do more interesting stuff with this. So one thing that we could do is we have a request coming in, and we know that we have to do subtasks. We have to do this task A and task B thing here. And so we can just submit that the tasks to the subtasks, submit that to this executor, and then wait for the results. The interesting bit here is that the executor that we're giving this to is a new virtual thread per task executor. It means it doesn't have a thread pool, which is what executors usually do. No, whenever you give it a task, it creates a new virtual thread and just lets it run. Right? And then you send that request, and then you submit those tasks, you wait for the results to get back, and then you send the response in this simple example. So virtual threads aren't faster threads. Each task takes the same time, right? It's not like some magic pixie dust that makes the CPU work faster. Like the computation always takes the same amount of time. Even the waiting takes the same amount of time. So each task from beginning to end usually takes about the same amount of time. So the same latency per task. So why do we bother about this? Because initially we talked about throughput, not latency. There's an article that I'm going to link later that compares parallelism with concurrency, something that was not on my radar at all. To me, that was always like somewhat convoluted, more or less the same thing. But concurrency means we have problems that are independently coming in at a timing that we cannot control. They appear concurrently, and we have to deal with them concurrently. Parallelism means we have a problem, and we think we can solve it in less wall clock time if we do more work, but in parallel. So parallelism is looking at how to get the latency down by splitting up a problem. Concurrency is looking at how can I get more throughput by solving each problem, solving more problems at the same time. And so when the workload is not CPU bound, then it makes sense that you want to start waiting as early as possible. Like if the CPU is done, like it's busy doing stuff, then you have to wait for the CPU to become free to do your own stuff, right? So that doesn't help. But if the CPU is not doing much, then and we're just waiting for the database, then it helps to just start like waiting on all these database calls or other system calls or file I/O calls as soon as possible. And that's what virtual threads are about, while keeping your code very, very simple, just like the run-of-the-mill regular code. So when the number of concurrent tasks is high and when the overall workload is not CPU bound, which describes a baffling number of Java services out there, then virtual threads will increase the throughput. Virtual threads are very cheap, I discussed that, and they're plentiful. You can have so many of them. And that means you have to learn or rather unlearn a few things. So for example, you pool threads because they're expensive. You don't pool cheap resources. So virtual threads don't need to be pooled. Whenever you have a new task, just start a new virtual thread with it. And that means we can also start think about new concurrency programming models. As predicted, the 60-minute talk didn't quite fit into 50 minutes. So I just want to leave you with the term structured concurrency. Keep that in mind. And then we're going to show you, well, OK. There's more on structured concurrency, is what I'm trying to say. At the end, there are links to structured concurrency and what they are about. And I invite you to go through this, because that's a very interesting thing that Loom makes possible for us. So just to close this down, virtual threads allow you to write simple code that's easy to debug and profile with high throughput, and gives you a new programming model, structured concurrency, that we have to skip. My personal guess is that virtual threads make it in JDK. My original guess was 20, but now Ron seems to be hell-bent on making me look bad, and it looks like it could be 19. So the JAP is proposed to target 19, and I expect in the next couple of days for the decision to be made whether it will actually make it into 19 or in 20. So virtual threads, you can already try them out now if you download a Loom early access build. But usually it's not you who controls thread creation, but your framework. And so like they have to change things as well on their end. So it's not easy to put it in production or like rather in a benchmark run, but hopefully you'll be able to. More links, as I mentioned. That has been for me. There's a book on the model system that nobody cares about. I mean, the model system is great, but just a book that nobody cares about. You can follow me, NipaFX, on Twitter, on YouTube, on Twitch, on nipafx.dev is my website. But also, if you want to follow Java, inside.java and dev.java are two sites that we recently put up. Well, Inside Java is actually a little bit older. And we are on YouTube, we are also on Twitter, and on GitHub. Remember, the OpenJDK is open source. Go to github.com/openjdk, and there's all the source code that you'd ever want to look at. Thank you very much. If you have any questions, you can just come down here and ask now or later. We have time now. There's a break coming.